Hello, good day everyone. So this is a recording of the topic Monte Carlo integrations and variance reduction. So the lecture will be divided into two parts. So the first part will discuss about Monte Carlo integration, and then the second part will talk about the various techniques in variance reduction, how to reduce the variance. So let's go to the first subtopic, which is on the Monte Carlo integration. So Monte Carlo integration is a statistical method which is based on random sampling. So we'll use random sampling quite a lot in these exercises. And Monte Carlo integrations is a numerical method used to estimate the value of definite integrals, especially in cases where analytical solutions might be difficult or sometimes impossible to obtain. So we'll see in the later on when we do the exercises, you'll see how do you want to use the Monte Carlo integrations to find out the estimated value of some of a certain variables of interest. So this Monte Carlo integration technique is based on the principles of probability and random sampling. And the basic idea is to simulate a large number of random points within a specific region, like from what number to what number, and then we want to use these points to estimate the integral. So the regions of integrations is defined by the limits of the integral. Say for example, if you have the integral of from 0 to 1, so that is what we call as the limit, and this is the regions of integration, and this is often referred to as the integration domain. So now let's look at this general example. So we let gx be a function, and suppose that we want to compute the integrations of this function gx over the two numbers between a and b, and we assume that this integral exists, otherwise we wouldn't be able to run the integration. So recall that if x is a random variable with a density given by fx, then the mathematical expectations of the random variable y equals to gx is given by, so the expected value of gx is given by the integrations of the gx fx dx. So if a random sample is available from the distributions of x, an unbiased estimator of the expected value of gx would be what we call as the sample mean. So now let's look at the first example, and in this case we are interested in to estimate data, where data is given by the integrations of the exponents of negative x dx, and then we want to compare this with the exact value. Okay, so first what we do is maybe we can, okay, so this one I just run through R. Okay, so let me just go back to the equation first. So this is the integrations of e to the power of negative x, and then this is we want to evaluate this from 0 to 1. So what we can do is, okay, that's the first example. We have deta equal to the integrations of 0 to 1, and gx is given by, in this case is e to the power of negative x dx. Okay, so first is we can evaluate this integration by itself, okay, in which we know that the integrations of ex or e negative x dx is given by negative e negative x, and then we will evaluate it from 0 to 1. So if we substitute the value x equal to 0 and x is equal to 1, so what we're going to have is going to have 1 minus e of negative 1, which is, if you try to use the calculator, you get the number of 0.6321. Okay, in fact you can also use R to get this number. So this is 1 minus the exponent of negative 1, and this is given by 0.6321. Okay, so this is when we want to evaluate this using integration, directly using integrations. So another way is we're going to use the Monte Carlo integration. Okay, so to use the Monte Carlo integration, the first one is we want to generate the random variable. So let's say we have generate x1 until, let's say for m replicates, we have x1 until xm, and make sure that this is IID from uniform distribution, okay, identical and independent distribution, and from uniform distribution from A to B. So in this case, because it's from 0 to 1, so this is uniform from 0 to 1. And then the second step would be to compute, so to compute the mean of gx, which is given by 1 minus m of all this gxi. And then finally, the estimated data is given by b minus a, which is the region of this one, and in this case is 1 minus 0, and then we multiply with the mean of gx here. Okay, so this is what we're going to do using R. So in R, okay, so first we want to replicate as as large as we want. So in this case, we want to use 10,000 replications. And then first, to make sure that your result will be similar to mine, so we use the same set yeah. And in this case, I just use set of 1, 2, 3. And then next is we want to generate the random number x, where x is given by the R-unif of m, where R-unif is the default or the command to produce random numbers from the uniform distribution. And because we just put m here, where m is equal to 10,000, so by default it will be between 0 to 1. And then next is the theta hat, and theta hat is given by the mean of these exponents of negative x, and okay, the value is, as we have seen before, it is 0.6333. okay, and we can see that this is the estimated theta. Estimated theta is equal to this theta hat, which is 0.633, and then this is by integration. So by integration, you have 1 minus the exponent of negative 1, which is equal to 0.6321, and the value is not so much different. Yeah. Okay, now let's look at the second example. In the first example, we evaluate the integrations from 0 to 1, and in this example, we want to evaluate the integrations from 2 to 4 with similar functions, yeah, which is the exponents of negative x. So we want to compute the Monte Carlo estimate of this function, and then we want to compare the estimate with the exact value of the integral. So first, in this case, again, we want to replicate 10,000 times. So m is set to be 10,000, and then we use the R-unif function, and in this case, we put the minimum equals to 2 and maximum is equal to 4. The default is from 0 to 1. And then in this case, okay, let me just use this one. So we want to compute theta is given by from 2 to 4 for exponents of negative x dx. Okay, so by integrations, this is what you have. You can have negative exponents of negative x, and then we want to evaluate it from 2 to 4, and this is given by negative 4, and then minus this one is 2, or you can just put it on the other way around. I think would be easier, which is the exponents of negative 2 minus the exponents of negative 4, and then if you use R or you use your calculator, the value that you're going to get is 0.1170. okay, so again, this is by integrations, and then using the Monte Carlo estimates. Okay, Monte Carlo estimates for this, just give me 1 minute. Okay, so first is, again, we want to generate m replicates of x. Okay, m replicates of x, so we have x1 until xm. So here we generate the random numbers and using the R-unif function in R. And then second one is, again, we want to compute the the average, which is given by 1 over m dxi, okay. And then finally we want to have the estimated theta, which is given by b minus a, and this multiply with dx bar, okay. And in this case you can see that we are evaluating between two numbers, which is 2 to 4. So this one is equal to 4 minus 2 and then times the gx that we're going to get from the random numbers. So this is what we're going to do in R, okay. So let's go back to this one. So first is we generate a random numbers. Our x is given by or x equals to our unif of 10,000, minimum 2, maximum 4, and the theta hat here is the mean of exponents of negative x multiplied by 2, because this is 4 minus 2, okay. So b minus a. And then the theta hat that we get from the Monte Carlo estimator is 0.1177. And then by integrations, we have the exponents of negative 2 minus the exponents of negative 4, which is equals to 0.1170, which is, the difference is just 0.0007. It's not so much different. Okay. So let us see, I think I will leave this as an exercise, so maybe you can do this on your own, okay. Maybe next time when we meet, we can discuss the answer to this one. And the next one, we are looking at another case in which this is related to unbounded problems. And in this case, we want to use the Monte Carlo approach to estimate the standard normal cumulative density function, which is given by phi x. And this is given by the integrations of 1 over the square root of 2 pi times the exponents of negative t squared divided by 2 dt. And take note that we cannot apply the algorithm above directly because the limit of integration covers an unbounded intervals, as you can see here. So this is evaluated from the negative infinity to a certain value of x. So the solution is, what we can do is we can divide this problem into two cases. So the first case is when x is larger than 0, and then the other one is when x is less than 0. And because we know that we have the knowledge of the symmetrical characteristics of a standard normal distribution, so whatever that we compute on x larger than 0, we can apply it for x is less than 0, okay. So I'm going to write some part of this into this one. So let me just clean this. So here we have the CDF of a normal distribution, which is given by the integrations of negative infinity to x, 1 over the square root of 2 pi times the exponents of negative 2 squared divided by 2, and this is evaluated on t. So in this case, we want to divide it into two parts, in which the first one is when x is considered to be larger than 0, and this is when x is lesser than 0. So in the case of x is larger than 0, then phi x will be evaluated at 0.5 plus the estimated theta divided by 2 pi, okay. And then when in this case where x is lesser than 0, and then this is given by the phi x is given, okay, so this is given by 1 minus the phi of negative x, okay. So the problem here is to estimate theta, in which theta is given by, and in this case we consider when x is larger than 0, so theta here is considered the integrations from 0 to a certain value of x, and this is the exponent of, because this part is a constant, so we're not really going to run the integrations of this part, so we just focus on t here, okay. So this is given by the exponents of negative t squared divided by 2 dt. Okay, so in order for us to solve this problem, it is easier if we replace t is equal to y is equal to t over x, okay. And then dt, so this is the the substitution in the integration, and dt is given by x dy. So here what we have here is theta equal to x of the exponents of negative xy squared divided by 2, and this is evaluated on y. Okay, so we're going to run the random number on y. Okay, on y. So what we're going to have is, in r, we're going to you're going to use u to evaluate on the y. So you can see here, okay, so this is theta, which is given by the integrations of x times the exponents of negative xy squared divided by 2, and theta, the estimated theta, is given by the sum of this divided by 1 over m, and here you can see that y is denoted by ui. Okay, and ui is the random numbers, and again this is the CDF when x is larger than 0, and this is when x is lesser than 0. So let's see how it is being done in R. So in R, first is we create 10 numbers for x, where x is a sequence, this one using the sequence function, the sequence from the number from 0.1 to 2.5. So what we have here is just this part of the standard normal distribution, because this in the middle is considered 0, so we have 0.1 and several other numbers, and then we consider until up to 2.5. Yeah, so for each of this value, then we want to evaluate. So x is considered to be a vector of 10, and then m, we want to have 10,000 replicates, and then u is our unit of m, and from 0 to 1, and then CDF is an empty vector. So CDF, we want it to be numeric, and then with the length of x, which means that we want to create an empty vector of CDF with 10 numbers, and then we're going to use the loop function to compute the CDF as well as g. Okay, so here you can see from I in 1 to the length of x, and we know that the length of x is equal to 10, because here you decide that x should be 10. First is you compute the value for g, where g is given by this. Okay, g is given by this x, x times the exponents of negative ux squared divided by 2. Okay, so x is equal to x times the exponents of ux squared divided by 2, and then the CDF is given by the mean of x. Okay, the mean of x divided by the square root of 2 pi plus 0.5, and this is because we are considering x is larger than 0, so the CDF is given by 0.5 plus the estimated theta divided by the square root of 2 pi. Okay, so we should have like 10 numbers, and each corresponding to the different values for x. The first one is 0.1, and then the second one, the last one is equal to 2.5, and then let's run this, and then you can see this is the Monte Carlo estimates that we have done just now. I'm so sorry, every time I highlight this, a prompt comes out. Yeah, so how do I want to, okay, I don't like this feature, so okay, so this is for each of the value for x. We consider from 0.1 and then 0.3 something and then up to 2.5. So in total we are considering 10 different values for x, and then this is the CDF that we get from the functions here. Okay, CDF, and this CDF is given by when x is 0.1, the CDF is 0.54, and so on. And of course, when x is 2.5, it is close to 1. And then what we want to do is we want to compare this with the exact value, okay, which is computed from the p-norm function, where p-norm is the probability distribution from normal probability for normal distribution. So p-norm is given by let me see, okay, it's stored as phi over here. So phi is equal to the p-norm of x. So each of these is corresponding to the value of x, and then we want to print them all together, And R bind means that this is a row bind, which means that you want to put X, CDF, and phi by row, yeah, and then each of the different value of X will be the column. And here we use the round function because we want to round all the numbers here to be like 3 decimal points, and we print it out. And as you can see, okay, so in the middle part, why I say it is middle, because we are evaluating this part and this part. So in the middle, what we can see is that the number is quite close to each other. So here from the Monte Carlo integration, you have 0.54, and then from the p-norm function you also have 0.54, but it is a little bit different when you go towards the end. But I think it's just like here is only one difference. Yeah. So the results for several values when x is larger than 0 are shown compared with the value of the normal CDF function p-norm. So what we see here is that the Monte Carlo estimate appear to be very close to the p-norm value, but the estimate will be worse in the extreme upper tail of the distribution compared to the middle ones here. Yeah, but overall I can see that it is not so much different. Okay, so this is another exercise. Maybe you want to do this so that you would understand better. So here I want you to compute a Monte Carlo estimate of the standard normal CDF by generating from the uniform from 0 to x distribution, and then you can compare your estimate with the normal CDF function p-norm. And then maybe you can do this on the phi of 2, and then maybe you can try to get the 95% confidence interval for phi 2. Okay. So how to get the confidence interval? We are going to cover this later. So now let us consider when we have the indicator functions, when we deal with the indicator functions like this one. So we let I dot be the indicator functions, and from the normal distribution z, and z is normally distributed from 0 to with the mean of 0 and the standard deviations of 1. And then for any constants x, we have the expected value for this indicator function when z is less than or equal to a certain value of x. So this is equal to bz less than x, which is given by the phi of x. And this can be evaluated at the standard normal CDF, and it will be evaluated at the value x. So what we can do here is we can generate the random numbers z from the standard normal distribution, and then the sample mean, which is phi hat, is given by the sum of all these indicator variable, which is the proportions of all the value of z less than or equals to a certain value x, and then this is divided by m. So this one will give you the proportions because it will evaluate for each of the z. If z is less than x, then it will be considered as yes. If no, then it will be considered as no. And then we are going to get this proportion. Okay. And we believe that this will converge with the probability of 1 to its expected value, where the expected value of the indicator of z less than x is given by the probability of z less than x, which is equal to the phi x. Now let's look on how this is being implemented in R. So first is we have x using the sequence function. We have x from 0.1 until 2.5 with a length of 10, and then we want to replicate 10,000 times. And z here, because we take z from the normal distribution, okay, z is considered to come from the standard normal distribution with a mean of 0 and standard deviations of 1. So z is R norm of m. So the dimension of x is given by the length of x, so it should be 0. Okay. And here p, where p, we use the apply function here. We have apply on the x, and then margin is equal to 1, and then fun is a functions of x and z. So here is like we have within the apply function, we want to use this function, which is the functions of two parameters x and z, where this function is given by mean of z less than x. So this one is corresponding to this yeah, the indicator function. So here what we do is we want to apply each function to each row in X. So we use margin is equal to 1. So that is the first one. And then in here, what it means here is that we calculate the proportions of the values in Z that are less than each element of corresponding row of X. So let's say the first one, the first value of X is 0.1, and then you compute how many of the Z is less than 0.1. Okay, let's say it's like 50% of all the Z lay below 0.5, okay, 0.1, and then you go on and on until the last one, 2.5. So as you expected that the probability, okay, the probability will change according to the value of X. So now let's look at the results here, okay, and again we want to compare this with the results of the normal CDF function P norm. So we have phi, where phi is given by the P norm of X. So the P norm is evaluated at each different value for X, okay. So now let's look at the P norm first. So this is the result from the P norm. So it is expected when X is equal to 0.1, then the value of the P norm will be, or the probability will be 0.54. And then the probability is going to be higher when X is equal to 2.5. And now we want to compare the value of the that we get from the normal CDF function with the value that we get from the Monte Carlo integration, and this is what we see. Yeah, so you can see that towards the upper tail they are very close to each other. Okay, in fact this one is exactly similar except for when X is equal to 1.967, and this is due to randomness. Probably you get a little bit different number from mine for this one, yeah, because we didn't use any of the set function before, but the pattern should be the same, where you can see that towards the middle it seems like they are very different. Yeah. So the conclusions here is that it appears that we have a better agreement with the P norm in the upper tail, but worse agreement near the center. Okay, and now we want to talk about the variance. Okay, so the variance of data hat can be estimated by the g of x divided by the mean of g of x and squared, and then divide by the number of replications m here. Okay, so this is a standard variance formula. So here what we want to do is we want to estimate the variance of the estimator. We're still using this examples here from the indicator example. So here we want to see how we can estimate the variance and then come up with a 95% confidence interval. And for this one we want to evaluate when x is equal to 2, and then another case when x is equal to 2.5. So let's see, first is when x is equal to 2. So we want to replicate it for 10,000 times, and then z is equal to the R norm of x, and g is the compute the proportions. When z is less than x, and then g will be a certain value, and g will be a proportion like 0.5, 0.6, 0.9 and something. Okay, and then here we have the variance. The variance is given by the mean of g minus the mean of g minus the mean of g, and then we take the square of this and then divide by m, and this one corresponds to this formula, and then the CDF is given by the mean of g. Okay, so here we can see that the expected value or the mean of g is given by this one, and then this is the variance, which is 0.0000213. Okay, and then we want to compute the 95% confident, because 95% confident corresponds to the z value of 1.96. So we get the mean, which is the CDF, plus minus 1.96 times the square root of v, where where v is given by this one, yeah, by this formula. So this is plus minus the square root of v. So the 95% confidence interval is given by 0.97 to 0.98. Yeah. And this this is just a normal C function. Yeah, so this is C because you want to combine these two together into one line. Okay, so here the probability of the indicator variable z less than x equal to 1 is given by phi 2, which is nearly 0.9782, okay, which is 9782 over here, and this is given by CD, the mean of G that you get from here. Okay, and then here Gx has the distributions of the sample proportions of ones in 10,000 replicates Bernoulli trials, with P is approximately 0.9782, and then the variance is given by this one. So how to compute the variance? It is the CDF times 1 minus CDF divided by M. Or you can just look at this. You can just look at this formula, okay, and then divide by 10,000, and then you have 0.00. You have to move this like 6 times, so it's 0.00000213. Okay, so for when x is equal to 2.5, we just change the value for x here, and the rest is the same. So we can see that the mean is given by 9.9. This one is 0.0993, and then this is the variance. And then again, to compute the 95% confidence interval, it is given by this one, where CDF is plus minus 1.96 times the square root of the variance. Okay. So this is the result of. Okay, so now we are going to move on to the next topics on the variance reduction. So previously what we saw is we have seen that the Monte Carlo integration can be applied to estimate the functions of the type, the expected value of g and x, or g of x. And in these sections we consider several approaches to reduce the variance in the sample mean estimator of data, where data is given by the expected value of gx. Now, the variance of the Monte Carlo estimator is given by the variance of data hat, is given by the variance of y hat, which is equal to variance of fgx divided by m. And from these equations, you can see that in order for us to reduce the variance, we have to increase m. Okay, the larger the m, the smaller the variance will be. However, when we want to increase m, we need to it relates or it involves the computing cost as well. Like in the previous example, we use 10,000, m equal to 10,000, but if you can increase more m's, then you can decrease the variance, but it involves some cost. And a large increase in m is needed to get even a small improvement in the standard error, which means that in order for you to increase m here, it will only result in a small reductions in the variance. So for example, to reduce the standard error from 0.001 to 0.0001, we would need approximately 10,000 times the number of the replicates. So therefore, although variance can always be reduced by increasing the number of Monte Carlo replicates, however, it involves the computational cost. So other methods for reducing the variance can be applied that are less computationally expensive than simply increasing the number of replicates. So the first two here is what we are going to cover in this lecture. The first one is the antithetic variables, and then the second one is the control variates. So this is like introducing another covariates in our calculation, and the next two is related to the sampling. Okay, however, for this class we will only consider this one, but if you want to learn more about the other two, then you can look at the textbook. So now let us look at the antithetic variates, yeah, and then what does it mean? I think there is a relation between the antithetic variates and also the control variates. Okay, so what does it mean by antithetic variance? So let me, if I want to, okay. So this is the standard Monte Carlo procedures, yeah. So we want to have x, which is x is a random number, and then we want to simulate x, and then we get the g of x, and then we can use the Monte Carlo estimate too, or the Monte Carlo methods to estimate the expected value of g of x. And for this one, you can replicate x like how many times? To xm, yeah. And for this one, the variance is given by you know the variance is depending on the value of m, the value of replicates here. So in order for us to reduce the variance, we need to increase the m. Okay, however, these methods would be inefficient because it involves computing cost. So what we can do, maybe we can consider what we call as the antithetic variable. Antithetic variable is when instead of having x, okay, or to get x is we have like u1 u2 until um, where u is actually the random variable. Okay, so instead of having individual u1 u2 and so on until um, so what we can do is maybe we can have like a pair, like u1 1 minus u1, and then this is the first pair, and then u2 and then 1 minus u2 and so on. Okay, so this one let's see what benefit we can get by having this pair instead of just the individual u here. Okay, so let me just go back to this one. Okay, by using the antithetic variance, the negative correlation between the pairs help cancel out some of the random fluctuations. Okay, so what does it mean here is that because here like if you look at the first pair, first if you have u1 and then the second pair is 1 minus u1, so you know that the relationship here is negative, and the relationship for all of this is negative, yeah. So this one is what we can manipulate. And also let us recall, okay, the formula for the variance, yeah, variance between two numbers. So let's say you have u1 and u2, and this is two numbers, yeah. So variance of u1 plus u2 divided by 2 is given by 1 over 4 of the first is the variance of u1, and then you have the variance of u2, and then you have the covariance, 2 times the covariance of u1 and u2. So this is the variance of two random numbers, yeah. So if u1 and u2 is independent from each other, so the variance, okay, the same thing here, is equal to 1 over 4 variance of u1 plus variance of u2. Okay, because if this is independent, then we will assume that the covariance is equal to 0. So it's just, you just have this, okay. But consider, okay, consider if u1 and u2 is negatively correlated, like in the case that we proposed just now. If you have u1 and then the pair would be 1 minus u1, and the second pair is u2 1 minus u2 and so on. Okay, and in this case you know that this is negatively correlated, and all of this, if this is negative, can you imagine what's going to happen to this part? Yeah, so if we can manipulate this relationship, we know that they are negative, so it will result in the negative value of this one. Then at the same time we can say that the variance between u1 and u2 when they are negatively correlated would be reduced compared to when they are independent. So in the Monte Carlo estimate, okay, in the Monte Carlo estimate, we would assume that u1, u2 until um are IID. They are independent from each other. Okay, so the variance looks somewhere like this. But if we can manipulate this relationship, okay, we can make them as negatively correlated, then maybe we can reduce the variance. So that is what it means. Yeah. Okay, so by using the antithetic variance, the negative correlation between the pairs help cancel out some of the random fluctuations, and this leads to reduce in variance or reductions in variance. So these reductions in variance allow for more accurate estimation using the same number of samples or fewer samples to achieve a desired level of precision. So we still have the same value, the same number of replicates, where m is still equal to 10,000, but by using the antithetic variance, we can show that we are able to reduce the variance. Okay, I think I have already explained about this earlier in the, in my handwriting. So what is the step to get the antithetic variance? Yeah, so first is we generate the random sample from the underlying distributions of interest, like uniform distribution or normal distribution. And then based on that, we create the pairs of random variable, where each pair consists of a variable and it is antithetic counterpart. Yeah. So the antithetic variable is generated by taking the negation or complement of the original variable. So one of it is like if you have u, then you may consider 1 minus u, something like that. And then the next step is we use the pairs of the variables, both the original and the antithetic, to calculate the estimator for the quantity of interest by combining both the original and the antithetic variables. And then we can calculate the average of the estimators obtained from the original and antithetic pairs. Okay, and then so now let us Now let us look at this example. Okay, we want to consider the standard normal CDF where phi x is given by this equation. So the Monte Carlo estimations of the integral phi x is implemented in the function mag phi. Okay, optionally mag phi will compute the estimate with or without antithesis. Okay, now let's just look at this one. Yeah, so we are going to use the function mag phi. Okay. Alright. So mag phi is a function of several parameters. The first one is x. So once we define what is x, and then it will straight away compute. And then r is we set r to be 10,000, and antithetic is equal to true. So at some point of time we want to use the antithetic, and then at another point of time we don't want to use the antithetic, so we put it by default antithetic is equal to true. Okay, so mag phi is a function. We create a function here, and then this is the starting of the function. So first later on we're going to use the mag phi like this. Yeah, mag phi, and then we put x. Okay, x is equal to a certain number. So mag phi is actually a function that we are going to define here. So what is in the body of mag phi? So first is we have u, where u is given by r unit of r divided by 2. So as you can see here, we divide the 10,000 to be 2. Okay, so u is r unit of r divided by 2, and here we have if. Okay, if it is not antithetic. Okay, if let's say here we want to put antithetic is false, okay, then this one will be computed. So v is given by the r unit of r divided by 2, which means that you can see here u is r unit divided by r divided by 2. This one also r unit r divided by 2, which means that if you put antithetic equal to false, then all the u and v will be r unit. Okay, both u and v will be r unit. Okay, so I hope this one is clear. Yeah, so here you have u and then you have v. So one part of the random variable is u, another part is v. So if it is not antithetic, then both of them are unif, which means that they are independent from each other. Okay. Else, if it is antithetic, then V is equal to 1 minus U. So again, I want to show this to you. So here we have like make phi function is a function of x. R we already set to 10k, and then antithetic, yeah? Antithetic equal to true. So this is by default. So if you want to use the antithetic, okay, if you want to use the antithetic, then U would be R unif, okay, R unif, and V will be 1 minus U. So we have U1 R minus U1, and then you have U2 1 minus U2, and etc. But if it is not antithetic, okay, if it is not antithetic, then it's going to be U is equal to R unif, and then V will also be R unif. So they are independent from each other because R unif are both independent random variables. Okay, so that is what it means there. Okay, and then next is we have the CDF. CDF is numeric, and here is when we create the empty vector, and this empty vector must be numeric with the length of x. Okay, so what is the length of x? We haven't really decided yet, yeah, so x will come later. And then within this formula, within this function, we have the loop function over here, which we compute the g and the CDF. Okay, so the g is given by x times the exponent of negative ux squared divided by 2. So this one is similar to the previous example that we have done before, yeah. So if I can go back, I think it is still related to this one. Okay, so this one where you evaluate it at x times the exponents of negative ux squared divided by 2. Okay, and then the CDF is the mean of this g divided by the square root of 2 pi plus 0.5. Okay, and then lastly we put the CDF here is that, so when you run the make phi function, it will report what is the CDF value. Okay, so now let's look at this. So here is just nothing will happen if you just run this. In fact, I can just run this, and then you can just run this. So you can do it like one by one, yeah, like make phi of x equal to 0.1 maybe, and then let's say I just put there, okay, and then the CDF that I will get is 0.53. So this is assuming that the antithetic is true. So let's say if I put antithetic is equal to false, okay, so this is without the antithetic variable. Okay, so now we want to evaluate at x equal to 0.1 and several other numbers. So here you can see that x is a sequence of sequence of 5 numbers. So you can see x is equal to 0.1, 0.7, 1.3, 1.9, and 2.5, and then we want to evaluate the CDF at each of these points. Yeah. So first is we have phi, which is from the p-norm function, and this is we want to compare this with the antithetic variates. Yeah. So first is we run the Monte Carlo estimate without the antithetic variates. So here we put make phi of x, where x is all these 5 numbers. Antithetic is equal to false. Okay, some of you might want to ask, is it okay if we just put anti? I think R is quite smart. So because when you when you define this function, you put it as antithetic, and there are only like 3 parameters here. So when you put anti, it already know that it corresponds to this one. So this one is the Monte Carlo estimates without the antithetic variance, and then the second one is with the antithetic variance. And then finally, we want to use the R-bind, which means that you're going to bind all the rows together. So first is we have the value for X, and then this is using the Monte Carlo estimates without the antithetic variables, and this is with the antithetic variance, and then the last one, this one is from the p-norm function. Okay, so you can see that in the middle part of the distribution, they're all the same when x is equal to 0.1, but they tend to be different as you go along. And towards the upper tail, you can see that the one with the antithetic variance have the probability is much lower than the other two. So the summary is the approximate reduction in variance can be estimated. Okay, so next is what we want to do is the approximate reduction in variance can be estimated for given x by a simulation under both methods, the simple Monte Carlo integration approach and the antithetic variable approach. Now let us see how the variance can be reduced. Yeah. So in this case, we have m is equal to 10,000. Okay, and then first is we create the empty vector where MC1, MC2 is equal to the numeric m. So this one is just like to create the empty vector. So both MC1 and MC2 will have like 1,000 numbers. So we want to evaluate the variance when x is equal to 1.95. Yeah. So here for I in 1 to m, which means that for I in 1 to 1,000, MC1 is given by the McPhee of x, where x is 1.95, and then we want to run it for 1,000 times. The antithetic is false, so this one is the Monte Carlo estimates. And then the second one is McPhee of x, where x is 1.95, and here we didn't put anything on the antithetic, which means that this is the one that used the antithetic variance. Then now let's see. Okay, we print the standard deviations of the MC1, which is given by 0.006, and then this is the standard deviations of the one with the antithetic variance, which is 0.0004, and we can see that a huge reduction by using the antithetic variance. Yeah. So if you want to know how many percent of reductions that we have produced, so we can take the variance of the MC1 minus the variance of MC2, divide by the variance of MC1, and we get 99.5%. So the antithetic variable approach achieve approximately 99.5% reduction in variance when x is evaluated at 1.95. Now, the second way to reduce the variance while trying not to bloat on the number of replicates is using the control variance. Actually, there is some similarity between the control variance and also the antithetic variance. Okay, so if using the antithetic variance, we try to find another variance which is negatively correlated with the one that we have. By using the control variance, we also want to manipulate the relationship between the pairs of this random variable. Yeah, so how it is different? So the control variance involve introducing a known and correlated random variable, which is called a control variance, to reduce the variance of the estimator. by choosing an appropriate control variable which has a similar behavior to the variable being estimated, the variance of the estimator can be significantly reduced. So the idea is to estimate the difference between the variable of interest and the control variance, as this difference has lower variance than estimating the variable directly. So we want to use the knowledge that we have regarding the relationship of this control variance in order for us to reduce the variance. So what are the steps involved in using the control variance? So the first one is you define the variable of interest, and then we identify a suitable control variable. So usually what we do is we look for a correlated variable which is known and can be easily estimated. And then we simulate both the variable of interest and also the control variance. And then we calculate the control variance estimator and then determine the control variance coefficient. And then we combine them. And then we use the control variance estimator to obtain the final estimate of the variable of interest. Okay, now let's look at this example. So we want to apply the control variate approach to compute data, and which data is given by the expected value of exponents of u, and this is given by the integrations of exponent of u du evaluated from 0 to 1. Now first, by using the integration, we can just run the integration. So this is the exponent of the exponent of 1 minus the exponent of 0. So you have exponent of 1 minus 1 is equal to 1.718. Yeah. So by integration, we know that this is like data is supposed to be 1.718. Now, how do we want to use the control variance in this case? Okay. So first is, if the Monte Carlo is applied with m replicates, then the variance is given by the variance of GU divided by m, where the variance of GU is given by the variance of E of the exponents of U, which is given by the expected value of the exponents of U times exponent of U become exponent of 2U minus theta hat, where theta hat is the expected value of EU. So this is like expected value of EU squared. Yeah. So this is equal to expected of E2U minus expected of EU squared. And this is equal to the exponent of 2 minus 1 divided by 2 minus the exponent of exponent minus 1 squared, and the value is approximately 0.242. Okay. So the natural choice for a control variate is from the uniform distribution. So let us consider the one that we take from the uniform distribution, where u is from 0 to 1, where for uniform distribution, the expected value, or the EX or EU in this case, is 1 over 2, and the variance for any uniform distribution from 0 to 1 is given by 1 over 12. Okay, so here we can see that the covariance between the variable of interest, the EU, the variance of EU and U is given by 1 minus 1 over half E minus 1, by taking this into account. Okay, and if you compute this, you will get the covariance equal to 0.1408. Okay, so remember that the variance of theta is given by this. Okay, and as you can see, this is a quadratic function. So the variance of theta is given by the variance of gx, okay, plus c squared of the variance of fx, plus 2 times c, where c is a constant. C is a chosen constant. So times 2c times the covariance of gx and fx. So if we can solve this, and then we put c on the left hand side, and then we have negative covariance of gx and fx divided by the variance of fx, and this is when the variance is minimized at c star. Okay. And in this case, because the covariance is given by this, okay, the covariance is given by this, and the variance is 1 over 12. So by taking 1 minus e minus 1 divided by 2, divide by 1 over 12, and then you're going to get this, yeah, negative 12 plus 6 of e minus 1, which is negative 1.96. Okay, so let me just write it to make it clear. So the covariance of E, U, and U is given by 1 minus 1 over 2, and this is E minus 1. And then the variance of U is given by 1 over 12. So C is minimized, okay, at covariance of EU and U divided by the variance of U, and this is negative, and this is equal to negative 1 minus 1 over 2 of E minus 1, and then this is divided to 1 over 12, and this is equal to negative 12 of 1 minus E minus 1 divided by 2, and then if you just put it the other way around, you get 6e minus 1 minus 12, which is equal to negative 1.69. Okay, so the control estimator is theta hat of C, which is given by the EU of okay, this is the EU of minus C, so this is the value of C, which is 1.69. So EU minus C times U minus 0.5. So for M replicates, okay, the M times the variance of theta hat C is given by the variance of EU, which is variance of EU minus the covariance of EU and U squared divided by var EU, and then you just plug in all this information inside this, and then you get 0.00394. Okay, so the percent reduction in variance using the control variate compared with the simple Monte Carlo estimate is given by 100 times 1 minus 0.039 divided by 0.2429, which is equal to 98%. So this is, in other words, the percent reductions of the variance is given by 1 minus 0.0039, which is 1 minus the variance of EU divided by 0.2429, okay, which is, this is the variance of the variance of EU, and this one times 100%, and then you get this one equal to 98.37%. Now let us see how this is being implemented in R. Okay. So first is we set M equal to 10,000 replicates, and then A is equal to negative 12 plus 6 times E minus 1, where this is the this is C star. So U is the R unit of 10,000 numbers, and then T1 is the simple Monte Carlo estimate, which is given by the EU, okay, and then T2 is using the control variance, and this one is given by EU plus C, okay, plus A times U minus 1 over half. So the mean from the T1 is given by 1.711, and then the mean using the control variance is given by 1.717, and then to see the variance reductions, you can take the variance of T1 minus the variance of T2 divided by variance of T1, So here you can see that the percent reductions in the variance is given by 98.3781, which is similar to the one that we calculated earlier. It's this one. Okay, so because this is the first class, to cover this topic. So the other topic would be this using the sampling methods, but it is not being covered now. But you can, the book is already given to you. So if you're interested, you can learn about the two methods. Okay. So I think that's all for the class. Thank you.